All right, so this is homework one, part C. Um, I added the question in here just so that I didn't have to go back and keep checking it, right? So this says a rectangular slab with a cross-sectional area of A relative to its edges is initially uniformly at 80 degrees Celsius. One side is perfectly insulated, the other is exposed to air, and is at which is at 20 degrees, right? So if we draw this out, see how well I can draw this here. Right, so we have this rectangular slab, um, and right, so this side here is perfectly insulated, right? It has an area of A, right? We have air over here. Um, we'll say um, the positive X direction is this way. So what do we know, right? Perfectly insulated means we're not going to lose heat on that side to begin with, right? But we know that it's initially at 80 degrees Celsius at time zero, right? So if we express that, we know that T at any X at time equals zero, right? Equals 80 degrees, right? We know that from this section here, right? 80 degrees, time equals zero. And then we know the air side that it is exposed to the air at a temperature of 20. So we know that here, this air, anywhere within the air at time equals zero equals 20 degrees, right? So when we look at this and um, we look at how the temperature will change over time, right? Because we only have our initial conditions of at time equals zero, it's 80, um, the block is 80, and the air is 20, right? So we have to look at how the heat travels, right? So we know heat is traveling this way because it's colder on this side than it is on this side, right? And we know that from perfectly insulated into the block, that is going to be conduction, and leaving the block will be convection, right? So first we want to look at conduction, right? So Q conduction, we know that this is going to be Fourier's law, right? So minus Ka dt dx. And right now we are going to evaluate from 0 to L, right? So we know this is evaluated at x equals L, right? Because that is where our heat is coming from, right? Now, since it's perfectly insulated, we know that this will be 0, right? So it's actually 0 equals minus Ka dt dx evaluated x equals L, right? So now we can move on to our convection, right, on this side. So the heat of convection equals, right, so we have some arbitrary height of the block times the area times the change in temperature, right? Um, so how we can draw this out, if we have a graph here, right, we have position and temperature. We can break this graph into 3 parts, right? Um, right, so we have our insulation here. We have our block, and we have our air. So since we know that this is going to equal 0, right? Our slope at any given temperature has to be 0 for the insulation, right? Because it's perfectly insulated, right? And then as we go into the block, we know that the temperature is going to decrease, right? And then as we go into the air, it is going to decrease even more, right? So we have our 20 degrees, we have our 80 degrees, and as it gets colder, right? As the block gets colder, we're still at a 0 slope over here, but our block and our air slopes start to decrease as well, right? This continues as you go down, right, to some point in which this will be a completely straight line, right? So our heat, we lose more and more heat or we lose less and less heat as the temperature decreases um, over time, right? And so our slope progressively gets less and less steep until eventually it is 0. So that is um, right. That is our um, that's how we sketch how temperature evolves over time, right? So as time goes on, right, we lose our temperature decreases. This is over time, um, and so as time decreases, right, we know that it um, it will get less and less steep until eventually it is 0. So if we move on to this next part here, right, we have a coffee in a glass cup, right? If we draw this out, right, so we have glass, we have coffee, we have insulation, and we have air, right? So we're gonna have 4 sections, right? So over here we have our air. Here we will have our insulation, then our glass, right, and then we have our coffee. Now, uh, this is along the same principle, right, as the block here, right? We have our coffee at T equals 90 degrees Celsius. And the air equals 20 degrees Celsius, right? So, how we can imagine this, right? So, previously we had conduction and convection. Now we have more layers, right? So, from our coffee into our glass, we will have convection, right? This is going to be Q convection. Then, from our glass to our insulation, we will have conduction. Then, from our insulation to our air, we have convection. So actually, through the coffee will be convection, right? And then coffee to glass is conduction. So we can write all these out, right? So we know, like we established up here, convection is HA delta T, right? So our Q coffee equals HA, and then it's the temperature of the coffee minus T1, right? So we have T1, T2, and T3. So Tc minus T1, right? And that's because it's convection. Now we have our Q over glass, right, which is going to be minus Ka times we have T1 minus T2 over the length of our glass, right? And that is going to be this length here. This is LG, this is LI, right? So that's how the heat changes through the glass, right? And then we have our insulation, right? So that again is minus Ka, and then it's T2 minus T3 over the length of our insulation, right? This value here. And then finally, we have our last convection, which is the Q of the air, which is HA, and then it's T air minus T3, right? So this is what we have, and when we look at this, right, we can put this all together into one Q, right? So we know that Q net has to equal all of these, right? So we can do QC, so equals QC, which is HA TC minus T1, which equals our QG, which is minus Ka, and this is K of the glass times T1 minus T2 over LG. And then we have our minus Ka, and this is K of the insulation, A, T2 minus T3 over Li, and then finally our HA, T air minus T3, right? And so when we look at sketching this out, like we did here, like we did up here, instead of just having 3 sections, right? Now we have 4. So we have our, or we have 5, right? We have our air, we have our insulation. No, we have 4, sorry. We have our glass, then we have our coffee, right? So coffee, glass, insulation, and then air. So we know that the temperature of the coffee right now is constant, right? And we know that glass is not going to insulate the best, right? So it is going to be a narrow or not a very steep slope, right? And then we get to insulation, which the whole goal is to lower the temperature closer to our outside, right? So we have a big drop off here, and then we end with a smaller drop off here, right? And this pattern continues as you move along, narrow to steep to a little bit less, right? And that continues until you get down to the bottom here where it will be 0, right? Just like how we had before. Start steeper and then progressively get lower, and that happens here until eventually it will be back to 0, right? And so we can actually relate all of this to Ohm's law, right? So if we look at Ohm's law, it's voltage equals current times thermal resistance, right? Or times resistance, right? So if we look at our 2 equations, we know we have minus or equal, or Q equals minus Ka delta T over delta X. Then we have Q equals HA delta T, right? So, right, if we look at it, this is actually the change in, right? And so we can notice that we have our change here and our change here. So we know that in this relationship, our delta T is what our delta V is, right? So we can rewrite this equation here as dt equals Q times 1 over HA. And so what is current here, right? We know that current is the thing that is moving, right? And if we look back at our graph, right? What is moving is our heat, right? So Q, as we move along, is moving, right? Our area isn't changing, our height isn't changing. It is just the Q, right? So our I has to correlate to our Q. And so that leaves our resistance at being 1 over HA, right? So this is for convection. Now, if we do the same thing for conduction, right, we know we have delta T, that's our delta V. We have our Q, which is our I, and then we have our delta X over Ka, right? And so this is our thermal resistance for conduction. Now, if we look back at our last problem, we have this big equation here. Let me just copy this so that I don't have to keep switching back and forth here. Right, we have this equation. And so if we look at it, we know we can do the same kind of principle, or when we're looking at our resistances, right, we know that our total has to be the sum of our R's, right? And so when we look at this, we have our convection, right? This is convection, right? So this, if we look, try and find the R of this, it is 1 over HCA, right? Then we move on, right, to the R of this next one. This is for conduction. This will be LG, right? That's our delta X over minus KGA. And we can keep going, right? So the conduction for this one, Li over minus KIA. And then finally our convection, 1 over HAA, right? So if we look, and if we're trying to find our R total, we know that R total has to be 1 over, so one thing you can notice before we write everything out, we have 1 over, or something over an area, right? So we can factor out 1 over A from this equation. Then we get 1 over A times 1 over H plus LG over minus KG plus Li over minus Ki plus 1 over HA, right? So this is our R total term. And if you look back, right, we can put this as an overall equation, right? We know our delta V. We have our delta V equals our IR. So overall, if we do everything as an overall, we know that delta V is our T. So that would be our T from the coffee all the way to our T to the air, right? We know our I relates to the Q. So our Q total, which was our Q net, right? That's this up here. And then we have our R total. So with this, you can then solve for your total Q, right? This is our total Q. We can solve for our total Q, which is correct, right? Just by reworking this equation where we get TC minus TA over R total, right? And if we look back at the problem, we had our TC, we have our TA, and all of these values, right, our length, our height, right, those are all values that will be given or you can find within a problem, right? If you're looking at a coffee cup, you can measure the coffee cup. You can find your total length. You can find your area, right? So this Q total value is now easily found by relating our our Q equations to Ohm's law, right? And so instead of having to look up a thermodiffusivity or a thermal conductivity, you can just look in the problem and find your height, your area, your length of different surfaces, and it is much easier to find your Q total. So that is how we do, or that is how the temperature looks for in a block over time and with glass and insulation, and how that relates to Ohm's law and um, how it is how the resistance um, relates to conductive and convective heat transfer. And then you can kind of see the expression that we derived for the heat flow, right? We have our Q, TC over T, or TC minus TA over R total. Thank you.